In this part, I'm going to talk about the evaluation. First, I'm going to explain if the performance for the distributed ERT is different from ERT. Then I will proceed to training and test it and explain a little bit about that. And then I will go to the classification performance measures that we use in our work. So uh, distributed ERT's classification performance would be the same as the ERT algorithm. The reason for that is what we need to select the decision node is information gain. And when we have the data labels after classification with decision labels from all the data records, then we can calculate the information gain. And we can select the decision node with the highest information gain. Data labels of all the records will be sent from computational nodes to the server, and the server can calculate the information gain for every decision node based on all the training data. So there would not be any difference between the performance of ERT algorithm and the distributed ERT uh, algorithm or method. Uh, for any supervised classification or regression problems, we would have training and test sets. We train a model with the training data, and we don't use the test data in this part or in this phase. And we finally, when we learned the model, we use the test set for evaluation. And if in the data set, the training and test set was not separated already, we need to separate it with the desired proportion. Usually we go with 70 or 80% for the training data and 30 or 20% for the testing data. But this can be changed. And one of the classification performance measures is accuracy. Actually, it is the number of correctly classified samples to the number of all samples that we have in the test data. And these are true positives, and this is true negative, and these two are false positives and false negatives. This is our test data, and this is the labels, the actual labels of the data. And this is the predicted class that was predicted based on our learned model. When the label, the actual label of the data is positive, and when the predicted label is also positive, we say that we had a true positive. When the actual label of the data was positive, and when the predicted label was negative, then we call this a false negative. When the actual label was negative and we predicted positive for that record, we call this a false positive. And when the actual label of the data is negative and we've predicted negative, we call this as a true negative. And based on the formula, we can calculate the accuracy. Here, the accuracy was 50%, for instance. But the accuracy is not a good measure always, especially when we have imbalanced data. By imbalanced data, I mean when we have, for one class, we have a lot of data samples, like this one for class 2 or category 2, we have 24 samples. And for one class, we have too little samples in regard to the other one. Here we have only one sample for category 1. So here when our classifier does not work properly, we may even have a high accuracy. For example, this classifier classifies all the data in one class, but the accuracy is 96%. So this is not a good classifier, but it is a high accuracy. So we cannot, when the accuracy is high in such data, we cannot be confident about our classifier. But here, when the classifier is better, then we have a perfect accuracy. So we use other measures because of such problems with the previous one. F1 score is a more reliable one, but it's not the only one that we use in machine learning. The F1 score is calculated like this. We have a measure called precision and recall, and F1 score is a combination of these two measures. This is a more reliable measure, but there are also other options that we can use for evaluation of the of our classifier. Thank you very much for your attention.